I hope everyone's awake. Everyone had coffee, right? Raise your hands if you're awake. Oh, there's a few people sleeping here. Please wake them up, okay? Okay, so today we're going to talk about what Docker does under the hood, and we have a lot of slides to go through. So, let's get started. As I said, I do crazy stuff. I built my own CDN, which the article for some reason made it to Hacker News front page. I experiment with programming paradigms, so I kind of try to combine functional and object-oriented programming. And what we're going to talk about today is what Docker does under the hood. And you will see why some people say that containers are actually not a technology. They're a combination of many things. I also started doing animated videos. For example, this one's about Ethernet, and there's one coming about Docker. So if you want to follow me, this is the place where you can do it. But I realized that my name might be a little difficult to remember since it's Hungarian. There is a very interesting language for you to learn, and it's completely useless because you can't use it anywhere else in the world. So I recommend that you just remember my nickname, Janoss Zen. And here's a little trick for you to get to my homepage. If you're using Google Chrome, just type in the address bar, just type @JanossZen, then hit Control Enter. And it's going to take you to my website. And I'll leave it to you to figure out why that works. Okay, so here's a little debugging challenge for you. What are we going to talk about today? So, first of all, what even are containers? What are they made of? Second, a little bit of containerization history, and this part was particularly hard to put together. Then we're going to talk about Linux capabilities, and I'll explain what that means in a minute. Linux namespaces, cgroups, seccomp, and finally we're going to talk a tiny bit about AppArmor. And at the end, I have a little demo for you, given that we have enough time, where I basically implemented my own containerization engine for demo purposes. If you go home and use it into production, don't sue me, it's not going to work. Okay? So, a few caveats. I'm not an engineer who builds Docker, for example. I don't write the code of Docker. I'm a DevOps engineer, I sit at home and I get mad about things. And usually what I get mad about is when people misunderstand what things are. And that's when I start writing articles or make talks like this. In that sense, I'm going to simplify a lot. So this is going to be a high-level overview of what containers do. It's not going to go into the details. And if I'm wrong, please feel free to correct me. And I know there's a few in the audience who can correct me, and we'll talk about that a little later. So what are containers indeed? It occurred to me when I started making this talk that a lot of people in the audience wouldn't know what MS-DOS is. Who knows what MS-DOS is? Oh, actually, we do have quite a few who actually used MS-DOS. That's fewer people. Okay, so initially, when we had our hardware, this was a machine, we could run one program on it. It started with punch cards, right? We punched it in the machine, and then on the other side, this little printer printed them out. But the problem was that at some point, the machine got too powerful to run just one program, so you wouldn't want to just do one mathematical calculation or just run one program like Word. You wanted to run multiple programs. So in order to coordinate that, you needed something. And this something in Linux is called the kernel. We'll talk about what this means in a moment. So you have two programs. How do you prevent two programs from messing each other's stuff up? How do you prevent one program from writing into the memory space of another program? How do you prevent one program from writing directly to the disk and formatting your hard drive and deleting all your kitten pictures? Well, let's see. Here's a text editor. Nice icon, right? And this text editor wants to open a file, /foo/bar. And whenever you open this file, it's making a system call to the Linux kernel. And the Linux kernel then goes ahead and reads it from the disk and reads the file system table and whatever it needs to do to open that file. If there's a second process, it does the same thing. It goes to the Linux kernel and it's going to open the same file. However, in Linux, we now have the ability, actually we had this ability for a long time, to separate this. So one process sees one folder or one file, and under the same name, a separate process is going to see a completely different file. And this is what Linux does under the hood. So we can do this with many things, like mount points, we can have separate users, we can have separate machine names, we can have separate network interfaces, process IDs, and a bunch more stuff. So how is this different from virtualization? In virtualization, you have one piece of hardware, you have the host operating system. The host operating system has its own kernel, and above that kernel are the programs that are running in user space. If you have a guest operating system, and assuming that you have a CPU that supports this, then it's going to run a separate kernel, a separate piece of user space programs on top of the hardware. So the CPU is going to do all the switching. However, you have to run an extra kernel, so the CPU has to work extra hard to separate these two, right? So there's a bunch of resources that are being wasted. Well, not wasted in that sense, but it's a complete separate operating system with everything that belongs to it. So a bunch of user space programs, etc. Containers, on the other hand, are not like virtualization. They're not something that the CPU does. It's not a separate operating system. Instead, a container is basically just one program running on top of, in this case, Linux, and I'm going to talk only about Linux today, where this program has, for some reason, a separate environment. For example, a separate piece of disk where it can write, or a separate piece of memory, or a separate process ID, a bunch of process IDs, etc. So in case we want to run a Docker container, we do docker run traffic, which is, by the way, an awesome reverse proxy if you're working with Docker. So what does this do? If you look at the process list with this highly unintuitive command, what are we going to see? First of all, on the host, we're going to see there's a dockerd. Under the dockerd, there's a bunch of other stuff, again, belonging to Docker. They use this for whatever reason. I wouldn't know. And inside the Docker container, there is one process. This process is called traffic. However, if you go into the container and you look at the process list, you're only going to see /traffic. So the container doesn't see any processes outside the container, but outside the container, you see everything inside the container. So that's how it's done. The traffic process is basically in its own PID namespace. So the process IDs are in its own little environment and it doesn't see anything outside. So containers are basically comprised of a bunch of technologies in the Linux kernel due to many, many companies doing a lot of work, and I'm going to talk about that in a minute. One is capabilities. The second one is Linux namespaces, for example, the aforementioned PID namespace. The third one is seccomp, which limits what system calls you can do. And there is a bunch of other technologies like AppArmor, SE Linux that help jail the container, the process running inside the container for example, to prevent a container from restarting the host operating system. That would be really bad. And of course, there's a bunch of other stuff, things that people have put into the Linux kernel to make it easier to separate environments. Okay, so a little bit of containerization history, and I really have to give a lot of thanks to Kier Kolschkin. He helped me a lot. He was one of the original OpenVZ developers, and he helped me a lot to get my facts straight, because I originally assumed that the whole containerization thing was coming from Unix, especially from BSD, but it turns out actually it came from much further back in time, from the mainframe area. So what we have here are three technologies. Oracle Solaris containers are actually a little younger. And we have Linux vServer and OpenVZ. Around the 2000s, these two projects, Linux vServer and OpenVZ, were two separate attempts of getting some sort of what we now call containerization. Back then, it wasn't called containerization, it was called VEs, or virtual environments. And what these technologies did is basically run more or less a full operating system inside of an environment, but without the help of a guest kernel, like you would have on a virtualization technology. And the goal here was to save resources. So for example, you could run your PHP application inside a VE, and that application could be limited in terms of how much CPU it could use, or how much disk bandwidth it could use, or even the disk space. These were called, by the way, user bean counters, and they didn't make it into the modern containerization system. So a lot of companies put a lot of effort, and of course the OpenVZ folks as well, to getting this into the mainline Linux kernel. So IBM, Google, OpenVZ, and SGI, which I think doesn't even exist anymore, and there was one other company called Bull, which I didn't even find a logo anymore. They put a lot of effort around, starting from 2006, of getting the OpenVZ features that allowed containerization into the mainline Linux kernel. Because with OpenVZ, you had to always patch your kernel, you had to compile it by hand, so it was really hard to use, and most of the time it really only worked on CentOS. Debian also had some level of OpenVZ support, but it didn't really work properly. So, for example, what we have for resource limits called C groups was a work of Google. They, as far as I know, they took apart the user bean counters from OpenVZ. And again, I could be wrong. History is really hard to research because nobody writes the stuff down. And they put it together back again, and then it was called C groups. It made it into the Linux kernel, and suddenly we had proper resource limit for processes. And you can use these outside of containers. So if you just want to limit one process, how much CPU it can use, you can just use C groups without containers, without Docker. And you know, once all these technologies made it into the Linux kernel, this happened. We got a bunch of containerization technology. It was like the 2000s when everyone wanted to do their own virtualization technology. Nowadays, everyone wants to do their own containerization technology. So we have Mesos, Kubernetes, Docker, LXC, whatever. I'm sure there's a bunch of other technologies. But under the hood, all these technologies somehow use the features in the Linux kernel. And you can do this yourself if you're crazy enough, like me. You can write your own containerization engine, which is going to be at the demo at the end of this talk. So, if you want to learn more about the containerization history, I recommend this talk, A Brief History of Containers by Jeff Victor and Kier Kolschkin, because they explain how this whole thing came to be from the mainframe era up to basically, I think the talk was in 2015, so up until 2015. So, let's talk about our first technology, capabilities. What are capabilities? So, on Linux, normally you need a root user to do important stuff. For example, kill a process that is not under your own user, or to format the hard drive, etc., etc. You need the root user. And there's a bunch of other things. For example, opening a port, so running a service under the port of 1024. And to do that, you need root. But sometimes you want to give a process the ability to do this, even though the process is not running at root. So here's a question to the audience. Can you run ping as a normal user? Who says yes? Can you run ping as a normal user? Okay. Who says no? Actually, you're both right. You know why? Because if you look at the ping binary, it looks like this, and it's even red in your console if you have console colors turned on. And the trick is the suid bit. The suid bit means that it runs as the user who owns the file, not the users who are running it. In this case, the ping process on Ubuntu, at least, is always running as root, because in order to make a ping, you need the capability to open a raw socket, and again, that's something that is tied to the root user. But if you have the CapNet raw capability, you can run this process ping under a non-root user. And there's another capability, CapNet Admin. This means that you can, for example, create ton devices. So if you want to, for example, run OpenVPN in Docker, you need to add these two capabilities, which basically makes the Docker container have these, even though it's not supposed to have them, because CapNet Admin allows the Docker container or the process running inside the Docker container to change around the network interfaces, and normally you don't want that. So there's a bunch of other capabilities. CapChown allows you to change the owner of any file, regardless of who owns them. This is also something that you normally, as a normal user, cannot do. You have CapCal, which allows you to kill a process. And this is actually, I think, going to be in the demo. We'll see in a moment. You have CapNet bind service, which allows you to run a service on a port under 1024. Normally, you would need to start your process, for example, your Apache or your Nginx as root, and then that process would switch to a non-root user after it has allocated the port. You have set UID and set GID, which allows you to change the user at will. This is, again, something that you normally would only be able to do as root. You have capsys chroot to run inside of for example, run your process inside an empty folder. Capsys nice to set the process priority of a Linux process, how much CPU it should get. And there is a bunch of libraries that allow you to do this. libcap, libcapng, and you can also use the system called prctl. The problem here is that if you want to program this yourself, this is bloody hard. So the problem, let's take a look at how this actually works. So we have a little bit of a C program. Any C programmers in the audience? Don't look, it's terrible. Okay, so int main. This is the high school example of Linux kernel programming. we're using CapNG here. So what we are we're clearing all capabilities out of this process, which means that even if it's running as root, it will have no capabilities. Then we're saying, okay, apply this, and then we can start a bash there. And what we will see is even though we're running as the root user, we will not have any capabilities. So we cannot, for example, kill a process or do a chroot or anything like that. The problem is that both libcapng and libcap2 are quite hard and quite limited. So if you want to actually do the whole containerization thing, you have to go with PRCTL, and PRCTL's usage is quite hard. Let's just put it that way. So I didn't actually manage to get a full containerization with capabilities to work. Okay, more fun topics. Linux namespaces. So let's take a look. Again, C code, high school example, int main. Then we do some stack magic, which I'm not going to explain here. It's first of all, because if there's any C programmers, we would need resuscitation here. They would need a hospital afterwards. And then what you do is the clone command. Who here has done C programming at high school or university? Okay, quite a few people. They might have explained to you that there's this function called fork, which allows you to start a separate process. Now, clone command, the clone system call, is what is under fork. So whenever you tell the Linux kernel, okay, please make me a new process, clone is what fork is actually using. And first of all, we pass it a child function, which means, okay, continue the execution there once you have the new process. Then we pass this stack top from our stack magic, which again, I'm not going to explain. I'm probably not even qualified to do so. And what we do here is we pass a bunch of flags. In this case, we are going to pass the flag clone new ns, which means new namespace. And we're going to say clone new net, which means please start this process with a new network namespace. And what this is going to do is it is going to start a new TCP IP stack, a new network stack in the Linux kernel. So this process that we just started will not have access to the host operating system's network stack. It will not be able to use the IP address, the network interfaces on the host operating system, etc. And then we do a bunch of other stuff and wait for the child, whatever. So this child function, how does it look? It just looks like this. We can pass it a bunch of arguments and it just looks like a normal program. So that's it, easy like that. So we have three system calls that we can use here. The clone system call is starting a new process, but sometimes you want to change the namespaces of an existing process. That's what unshare is for. And the third one is set ns, when you want to join an existing namespace. Why is this important? Because as sysadmins or DevOps people, how we're normally called nowadays, you can use this. For example, let's say you have a traffic running, a container with traffic. How do you debug it? There is no bash in there. You cannot docker exec inside that container. So what we're going to do is do a variable. Target is equal to whatever the container's name is. And then we're going to do a docker run. The docker run is going to take, in this example, my debug image, which just basically contains a bunch of tools for debugging. And then we are going to say, please use the PID namespace of that other container. So you're basically running two containers in the same PID namespace. And we're also doing the same for net. So if you want to TCP dump inside a container that doesn't have TCP dump installed, you just launch your debug container inside the same namespace as the target container that you want to debug. And that way, you add a bunch of capabilities, so you can add extra permissions to that debug container, and now you can suddenly debug something that you previously couldn't because there wasn't any bash in there or anything like that. So, oh, someone's battery is going down apparently. So the reason why we need to know about this stuff is because it enables us to do our work better. So if you do use the namespaces and the capabilities, we suddenly have a debug container. So number 3, or actually number 5, counting, math. I was never good at math. So C groups. What do C groups do? First of all, if you look at your mount points on your modern desktop Linux, for example Ubuntu, you see a bunch of mount points called C groups. In this case, you see a C group on sysfs C group CPU set. And the CPU set is one of the aspects of limiting resources. In this case, CPU set means that you can specify a certain process which CPU cores to run on. So if you want a process to only run on that specific CPU core, CPU set is your friend. So we can create a C group like this. This is a utility called cg-create. Obviously, there is a bunch of system calls and whatnot, but this is probably easier. You just tell it to, hey, let's make me a CPU and CPU accounting in /my group. And these groups are, you can put groups in each other, etc. So there's a bunch of other things that I'm, again, not going to talk about today. So once we have our C group, we can basically say, look, we want to classify a certain process that is already running into that C group. So we take our process ID, which you can see on the right, and put it into that C group. And suddenly all the limitations that are applied to that C group are applied to that all the processes together running in that C group. And then we're going to be nasty and limit this process or all the processes in that C group to only run on core 2. And we do that by simply doing echo 2 inside that file. So it's basically a file that we can use to manipulate C groups. Again, there's a library, etc. So what kind of C groups are there? These are just a few examples again. CPU set.cpus for CPU cores. Shares, CPU.shares means, okay, out of 100 shares or 1000 shares, how much CPU bandwidth does that process get? So for example, if you want to give it 10% CPU, you set it 10 shares out of 1000. You can also do real-time scheduling. For example, if you have a kernel compiled with real-time features, then you can do stuff like, okay, I'm going to schedule in 100 millisecond increments, and out of 100 milliseconds, this process is only going to get 10, or however much you want to give this process. So that enables you to do real fine-grained scheduling for certain containers. And Docker actually has to work on this one because C groups are possible, resource limits are now possible with Docker Swarm, but with Docker Compose, they took it out of version 3. So Docker folks, please fix that. Same goes for memory. We can do a limit in bytes. We can do another type of memory. So one is with caches, the other one is without caches. You can read all this on the proper man pages. Then we have BLK IO, which means how much bandwidth it is going to get towards the disk. In this case, it's in bytes per second, and you have the same for IO per second. Okay, last one on the list is seccomp. So you notice we did all this other stuff, like for example, limiting how much bandwidth it has towards the disk, what it can access, etc. We didn't do one thing. We actually don't have a hard limit on which system calls the container can use. So there are a bunch of dangerous system calls, obviously. So how does seccomp prevent using dangerous system calls? Again, we have our text editor, and it's going to talk to the CPU. So the CPU, in the old days, you would basically instruct the CPU, okay, go there, read that from the disk. When we have an operating system, the text editor goes to the CPU and says, oh, please read from the disk. And the CPU says, nope, sorry, can't do that. Instead, what the text editor has to do is actually call the kernel, and the kernel can then go to the disk and ask it for stuff like this. So this one is called a system call. And the way we use it, in this case with libseccomp, is we basically have one call that says, okay, initialize the seccomp profile. In this case, our default profile is going to allow everything. Normally, you wouldn't want to do that. Then you add a rule. For example, if someone calls the bind system call, then please kill that process. So that's going to do the axe to head method. But you can do stuff like, okay, please make a callback so you can do proper logging, etc. And finally, you say seccomp load. And afterwards, if you try to use the bind system call to, for example, do a telnet, which we're going to see in the demo, then you will see that it will not work because the kernel is going to say, nope. Okay, last one, AppArmor. AppArmor, I'm not going to talk much about this. This is basically a role-based access control. You can do stuff like, okay, this AppArmor profile and any processes running with this AppArmor profile cannot open raw network connections. You can deny or allow mounting. You can do the sysrq. You can allow or deny the sysrq trigger, which is used for reboots. So it would be really silly to allow reboots inside a container. You can, for example, add capabilities like the set user ID, and that's about it. You can read up all this stuff. So what we're going to do now is what they usually don't recommend for talks, is a live demo. So if I'm going to screw this up, well, I'm sorry, I'm not a C programmer. Let's see how this goes. What I prepared here is a Linux virtual machine because I'm not brave enough to run this on my own operating system. And if we look at this little output, I have this repo on GitHub. You can take a look at it. I made a demo for the different aspects of containerization. So for example, we have capabilities, namespaces, and seccomp. Let's take a look at that. It's basically a little C program. Let's start with namespaces. What I'm going to do is I'm going to take a look at the network namespace. And what we have here after compilation is one binary. Going to run this demo. And it's telling me, okay, now you're in a bash that's in a namespace. And you see I'm still root user and everything. But if I now do ifconfig, there are no network namespaces. There are no network interfaces here because I'm in a separate network namespace. If I go out of this bash and do the same, you see I have a bunch of interfaces here. Inside, there's nothing. I could, of course, create virtual network interfaces to connect to the host machine, and that's what Docker does, to put into a bridge. But if you run a network namespace, you have a completely separate network stack. Let's take a look. What else do we have? We do have a PID namespace. Let's take a look at the PID namespace. If we now run this dreaded command, it shows us a bunch of processes. However, if you run the demo, I'm now in a bash inside of a PID namespace. And if I run the same command, there are no processes. I only see the processes inside that namespace. And the same thing is true for a bunch of other stuff. So, for example, you can manage mount points separately. You can manage host names separately. Again, the concept is very similar. In order to make these work, you just have to read. You just have to have too much time and be too angry to read the Linux, the LVN articles about this. So it's basically just research, but it's not very complicated. Let's take a look at seccomp. In seccomp, I'm going to run this demo seccomp, and that's again going to launch me inside of a shell that's in a seccomp profile that has the bind system call disabled. So it already tells me I can run telnet google.com AT. So if I now run this, it's broken. Hello. Oh, I have no internet, so it can't even do a DNS lookup. Whoops. Please connect the Wi-Fi. Will we have this running in a moment? There we go. So let's try this again. Still no internet? Okay, so this demo you'll have to look up on your own. I'm sorry about this. Trust me, it worked before the presentation. So capabilities. Actually, no, let's do the proper container runtime. So what I did is I put all these separate aspects of containerization inside of separate folders. All of them have readmes. So if you want to read how these work, you just simply have to go onto GitHub and read the separate readmes for each of these aspects. They're explained in detail, so you can mess around with this. But again, if you go home and tell your boss, "Oh, I now need to write my own container engine," sorry, but that's a really bad career choice. Trust me. Unless you work for Docker. Okay, so how does the runtime work? The runtime unifies a bunch of aspects of containerization, including I have a container image. This container image contains an Alpine Linux. So let's take a look at this. Go to runtime. No, actually test container. If you look here, I have a tar GZ with the Alpine Linux. And I'm going to put this into an image file. The script is really easy to build this. So it's basically just going to create a file that has a file system in it, an X4, and I'm going to mount this using a loop device. If you don't know what that means, don't worry, I'll show you in a minute. So basically just pack Linux up, put it into a file, and then we can mount this as a container root. So, assuming this works, I have to cheat and look at my own README because I don't remember how to run this. So I'm going to do demo runtime, test container image that I built previously, bin slash sh, and I'm in a container. So I have only my own processes, I have no network interfaces, and all the other aspects. So there's only one question left to be answered. yeah, first of all, you can find this stuff on my GitHub, so feel free to play around with this. And yeah, don't try this at home. So are containers secure? And that's not a question that I'm qualified to answer. So Phil's going to do that in this room right after the coffee break. And it's time for questions.